Hey guys, sorry for starting a little bit late today. It's 5:04 in the morning. I'm 4 minutes late. No excuse for that one. Just overslept. Yesterday there was an excuse. I don't know what happened, but no. That just happens sometimes. So let me go ahead and check on Twitch to make sure I'm live. I think I am. Usually when I start streaming from there, yep, everything seems good on my end. So hey man, what's up? So what are we doing today? Well, today. You may have noticed here, let me just flip back over there, the tag has changed a little bit for the stream. So it's Computer Coloring 101, Programming. We're not doing very much physics today. Today we're applying some of the, some of the stuff that we learned in the past few days to a new system, which is color, right? So the idea here is that let's say we have a picture with, full, as many colors as you could imagine. Well, in order to store all of these colors, we have to do something to them, So what we need to do is, let me see. How did you plot your Octree with new plot? Oh, yeah, sure. Here, let's go ahead and open that up. So let me go into CD Projects, Simuleos, and Barnes Hut. The command is enough. Kind of. Okay, so there's two things I need to show. Let me CD Projects, Simuleos, and of course Barnes Hut. And we go over here into, what do we have here? Yes. Oh, let's remove star.dat for a second. Remove star.dat. Too many files. Okay, now let's do ls. And we have two things here, vi cubeplot.gp. But you'll note that, hey Zadiston. Okay, so you'll note that we have splot octree 0.dat. U123 with lines ls1 lw2. So this in and of itself is not particularly useful, but that's what we have. The important part is here. So let me go into vi Barnes Hut. 1 second, lowercase Barnes Hut.cpp. I was supposed to give you this yesterday. Oh, good. Yeah, I was wondering where that was. We ended up using another force integrator yesterday, and that definitely helped out. Good. I'll take a look at that after stream and we'll see what's up. Let me see. X naught V naught T. Yeah. We definitely need to update A as it goes along. Yeah. Okay. Oh, sorry for that. Okay, so Avaze, the important part is down here. Here it is. So when we're outputting the data, we actually output it into a cube format. So what we do is I kept track of the lower left vertex, which is just one of the vertices in the cube. And, oh, actually, I think I kept track of all the vertices. Yeah, lower left vertex. Oh yeah, lower left vertex, X, Y, and Z. And then what I did is I output that, and then I output one box, another box behind it, another box on the side, and another box on the other side. So you'll note that we have 1, 2, 3, 4, 5, 6 outputs here, where 6 is just new lines. So 1, 2, 3, 4, 5. So 1, 2, 3, wait, 1 second. 1, 2, 3, 4, 5. So all 4 dots. And then the fourth dot twice. So all the vertices in a square, and then the fourth dot again. So that's 5. And then I just drew lines between them. So Octree 0.dat. Basically looks like a whole bunch of points. Here, let's go ahead and run it one more time to show that. 1 second. We go to the top. And let's just run it for a single time step. Write this, go over here. Right quit, make. Okay, let me ls. We should have an Octree 0.dat. vi Octree 0.dat. Oh. Let's run it for like maybe 5 time steps. Make that. Okay, now let's ls vi Octree 0.dat. You don't know why anything's not there. 1 second. 1 second. Not exactly sure. Oh, I know what's happening. We're not actually outputting any data. Here, let me go over here real quick. Let's make that. Okay, now let's go into Octree 1, and here's what we got. So, we have all of the positions for each of the cubes. So 1, 2, 3, 4. These are all at 0, unfortunately. But, yeah. So down here, they aren't quite at 0. So hopefully that makes a little bit of sense. Then what we do is we go into, sorry for the yawn. We go into each of the individual boxes. So we first output the big box, the giant box that encompasses everything, and then we go further into it by doing a recursive search further in. So I guess if we go down to Octree output, that will kind of, here. So after all that, we then go and do recursively outputting, there should be 2 T's there, everything else. And that's how it's done. It's actually not the easiest thing, and while I was writing it, I felt kind of silly because it's just such a long thing. But I don't know, I couldn't really think of a better way to do it. So that's how it is. Let me go ahead and go up and comment out some stuff, and then we'll get started on what we're working on today. By the way, guys, I do want to point out something. If you are interested in watching any of my live streams from, oh, I don't know, the past 2 weeks or whatever, you can do it in 2 ways. You're gonna like this. So here's my channel. You can go here, go down to, let me see, should be profile, past broadcast or something like that. Let's see, yeah, past broadcast right here. There you go. And you have access to all of mine for the past 2 weeks. You could also go to my YouTube channel, which is, again, linked at the bottom of my stream. Let's see, right over here, go to info, go down to the bottom, click on my YouTube channel right here, and you have access to all the streams forever since, well, okay, not forever, but since we started the, oh, what's the oldest one? Oh, I don't know what the oldest one is. Let's see, date, oldest, oh, the Submachine webcomic stuff. So, yeah, sure. A whole bunch of stuff back there, starting from back when we did the determinate visualization, some DMRG stuff like that. However, there is one more way to find my channel, which is actually kind of silly. So if you go to creative, and we just do a /physics, you'll find, under videos of all time, you'll find all my videos here too. And some other guy who's streaming on physics. But all my videos right here. So in case you don't remember my channel name, you can always go to creative #physics and you will find my streams. Except for these two, because I'm not streaming under physics for these times. Okay. So now let's go ahead and describe the problem we're working on today. Sorry, I know we were kind of behind the times, you know, sure. Okay. Give me some time. Okay. So before this, we were working on Octrees. Okay? Octrees. Today we're going to work on an application of Octrees. An application that is, well, one of the most used applications of Octrees. In fact, if you just Google Octree, let's go over here, Google Octree, and you go down to the Octree Wikipedia article, obviously I've clicked before, you'll see, okay, we have some example code for point decomposition, which is what we were doing before. And then immediately after, you have an example of color quantization, which may in fact be the most typical application of Octree codes. So I kind of decided, let's do it. It's not particularly difficult. It's not a particularly difficult code to write, and it makes a good bit of sense. So how does it work? Well, before we had all of the particles in some sort of XYZ grid. For now, I'm just going to put an XY grid, so some sort of XY box. Okay? We had a whole bunch of particles on this box, something like this, and we continually split up this box over and over and over and over and over and over again until all the particles had their own box. Something like this. I don't know, something like that. There we go. Those two particles are going to be kind of annoying to split up. That's okay. There you go. Okay, something like this. Forgive me, I'm really bad at drawing, whatever. Okay, so now, this is along X, and this is along Y. However, what if these weren't along X and Y, but along two different color spectrum of R and G? And you could imagine B floating out over this way. Okay, so we changed our coordinates to now be colors, right? Hey, Gustorn. So in this way, we can actually take all the colors in our picture. We can plot them as RGB values. And then all we need to do is find the center of mass. Hey, Titley, thanks for coming in. What am I saying? Oh, then what we need to do is find the center of mass of each of these boxes. So like we'd have the center mass for the big box up here, and it would be some RGB value. Then we have a center mass for each of these guys. So for example, the center mass of the big guy might be blue, somewhere in here. Center mass for each of the next guys might be maybe here. Actually, probably definitely not there. Probably here, 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 something like that. And then the smaller ones might be, I don't know, here, here, I don't know, here. I'm just drawing random dots here. And then as we go further down, you can see the center mass of each individual box. The idea is that each of these represent a different color, right? So what we've done is we've kind of said, okay, all the reds are maybe to the right, all the greens are kind of up top, all the blues are kind of this way, right? And so we have all of the colors kind of dispersed in this pattern. And then we say, okay, now we're going to go back through the image. And if we hit any particle that is within this box right here, we're just going to assume it is this red color. So if we pick, let's say this dot right here, all of a sudden this dot becomes the red color here. And so in a way we have quantized the color. We've taken all of those colors that were, you know, all the colors of the rainbow, and we've said, okay, we're going to approximate your color as the center of mass of the entire box that you're in. And this is kind of how we do the color quantization. We kind of cheat a little bit, and we say, okay, if you are within this box, you are this color. This means we could take as many colors in the rainbow, and we can, well, approximate it as 8 or as 64 or something like that colors, right? And that's kind of the idea here. It's relatively straightforward. It's a pretty good application for Octrees. And all we have to do is read in an image, check every single color, plot them on a graph, create an Octree for that, and then write everything out with using their center mass colors. And that's literally all we need to do. It's that simple. So if you have any questions, let me know, because I know I said it was simple, but you know, the truth is everything's simple when you know what you're doing, right? So again, if you have any questions, let me know. We're going to see how far we get. I've got a feeling we can finish the whole thing up today. But hey, you know, I'm never a really good judge of time. I don't think anyone who does a lot of programming is a good judge of time. So, well, maybe they are. Maybe I'm just bad at it. But if you have any questions, let me know. I'm going to get a quick sip of water, and then we can go ahead and get started. 1 second. And of course, guys, same rules apply as always. Feel free to talk about whatever you want in chat. There is very few restrictions there. You guys typically talk about some super nice things. It's actually kind of refreshing to see you guys do a whole bunch of really in-depth discussion in chat that I know nothing about. One more thing. I think one of the best skills you can develop as a programmer is accurately judging how long a problem is going to take. Maybe that's true. But I've just got a feeling that it's hard, you know. It's like it's not a trivial thing to figure out. Quit. Okay. So what do we have here? We have our old Barnes Hut code. So usually for me, I know how long it would take in an ideal world. Like I can say, okay, this will take about a week, and then I just, you know, kind of multiply that by some arbitrary factor. So like for example, at work, I said, hey, I think we can get this done by the time, I don't know, you get back from a trip or something like that. And that's what I say. And then I say, but chances are there's going to be a couple bugs, so I'm going to add a couple days to that. And honestly, it's pretty accurate. I'm not that far off. You know, usually a day or two off at most, which I know sounds like a long time, but you know, my deadlines are kind of up in the air right now, so it's okay to kind of be that off, I think. But there are a couple other times where I've had to approximate the time it's going to take for me to do something and I say, oh, it's going to take a week, and it takes like a month. So that's the thing though, like I'll say like this group of 3 things will take me a month, and it ends up being the 2 things that I thought were difficult end up taking me no time at all, and the one thing I thought was easy takes me like the rest of the month. One last thing I do want to point out, guys, is Rocket League for Linux was output yesterday. Was released yesterday. So if you guys are interested in that kind of thing, feel free to play that game. I just wanted to point out that it is now available. So we're going to make a new directory, and it's going to be color quantization. Okay, let's go and cd into color quantization. In fact, I do have Rocket League for Linux. I was thinking about playing it on this channel, but I don't know. After playing it for like 30 minutes, it wasn't really my game. I'm not saying that it's not a good game. It is a great game. It's just, it wasn't my game. I don't really like, I like multiplayer games, but I don't like it when I don't know the people I'm playing with, because it makes me feel kind of bad when I'm, you know, holding the team back or something like that. I'm just not very good yet at the game, so it's one of those things. Okay, so let me go ahead and move a couple guys over here. So we're going to move back the Barnes Hut makefile, just because, hey, why the heck not? Oops, over here. We're also going to move, let's see, vec.h. Oh, sorry about that. Barnes Hut and vec.h, because we're going to need it anyway. And then we're going to CP Barnes Hut over here too. So let's do Barnes Hut and Barnes Hut. Okay. Now again, we've already done our makefile. We've already done the Octree generation before, right? So we just have to do a simple modification of that. We're also going to need the Octree output file, or Octree output command, which we also have, and a few other things. So it's kind of useful, I think, to have this information down. Now, in terms of visualization, for color quantization, man, sorry for the yawn, guys. For color quantization, I think we're going to be using Blender for that, because we have everything set with Blender. It shouldn't be so bad. So what I think will probably happen, if I'm not completely off my rocker here, we'll take today to implement the actual algorithm. Again, won't take very long. And then we'll spend a little bit of time doing visualization, and we may do that off camera, or I might do that off camera. I might take tomorrow off. Again, it kind of depends on how I feel tonight, so I'm letting you guys know that ahead of time. It is the weekend for me, so I kind of take some liberties on the weekend, and I say, hey, look, I might not stream over the weekends, but every weekday I usually try to be up and streaming at 5 o'clock in the morning, and go from there, right? But for some reason, I've just been incredibly lethargic. You know, I've just been tired. And it's not been... I don't know why. I just have been. So let me go ahead and make it over here just to make sure everything is good. BarnesHut.o needed by Barnes Hut. 1 second. BarnesHut.h is what I need. Sorry about that. Let's go ahead and quit here. Let's move Barnes Hut. And of course, BarnesHut.h. And let's move it over here. Now let's try make, just to make sure we have all the appropriate files. No rule to make BarnesHut.o. What do you mean? Vec.h, BarnesHut.o, BarnesHut. What am I missing? Let me go over here. Let me do a quick ls. We have cubeplot.gp, but that's not too important. BarnesHut over there. Octree out.dat. Let me just remove all the .dat files. It looks like. Let's remove BarnesHut. Remove a.out. Remove star.dat. Make. ls. Barnes Hut. Oh, did I move the make file over here? 1 second. Let me move. I think I typed in move instead of CP. Right, quit? I did. Dagnabbit. I gotta CP them over here. 1 second. Let me now do CP. Color quantization. BarnesHut.h. Period. I always forget the period. Then we do make file. Here. Now let's do make command. Failed error. No such. Okay, let's do vec.h. I apologize, guys. Here we go. Now let's make that. Good. Okay, this one seems to make just fine. So here's what I'm going to do. I'm going to ls. I'm going to go over here. I'm I'm going to do make clean, and then I'm going to do another ls. That's the minimum that we need. So let me just do this. cp dot barns hut star dot. Okay, now let's make that. It makes just fine. Good. Okay, so now what are we going to do? We are going to modify everything. So let's go into barns hut.h. Actually, let's see. We don't need everything, so let me go ahead and cp barns hut.h into color quantization .h, and let's go ahead and cp let me see, barns hut.cpp into color quantization .cpp. Okay, now let me ls. Hey guys, I've got a question. So is .cc the newer or older version of a C++ file? Does that make sense? Like, I see a lot of people using .cc instead of .cpp, but I'm not sure, like, is .cc the old standard or the new standard? I know, like, I should be using .hpp for the header files, but I always just don't put the pp at the end. And it always seems to work just fine because it's a C-style header file instead of C++ header file, but I don't know really the difference there. So if you guys know, feel free to answer that one. So let's go into first color quantization .h, and let's modify that one. So here we're going to go here and change color quantization .h. 1 second. I know I don't have to, but I thought that it was better to use, or like more standard to use .hpp. Okay, let's go down here, change this to color quantization. That is then. Let me go to color quantization. Here, let's also put it there. Let me see. I would love to answer you, James, but I'm afraid to be picked on by Gustrum the bully. Hey, Frank, Gustrum's not a bully. Okay, so what do we have here? We have struct particle, we have struct node. All this seems okay. In fact, we could probably just keep everything in here, with the exception of the RK4 and Verlet algorithm. H is pretty much the standard header file format. Some people prefer HTTP for headers with templates. Oh, I see. That's fair enough. Okay. So what are we doing here? Why do we have a template here again? Let me see. Traverse post order, current constant function t. 1 second. Okay, we read in. Why am I so tired? I am the most tired person in existence. That's not true. But, you know, it could be true and you guys would believe me. Okay, so let's do color quantization.cpp. Quantization.cpp. And we include color quantization.h. Let's go down here, color quantization. 1 second. Okay. Right quit, vi makefile. And let's go down and modify this guy, and then we should be done with the modifications. Color. Yeah, thanks. Quantization. Here. Let's go down here, color quantization. There. Okay, and change this to color quantization.h, and then we should be able to make it. Quantization. There we go. Run quit. Make. Okay, seems to make just fine. Let me do a quick ls to make sure everything's good. Now let's do a make clean. ls. Okay, everything seems okay, except for some reason it didn't remove. Oh, let's remove barns hut. I guess star. Now let's make that. Barns hut error 127. Shoot. ls. 1 second. Oh, I know the problem. Let me go to the make file. He's not picking on anyone on the stream, Frank. He's actually like super helpful. So if you could tone it down just a second, that would be great. Now let's make that. Make clean. Make. Okay, that one seemed to run just fine. Good. So now we have the color quantization, well, skeleton all in. Now, let's go ahead and figure out what we need to do from here. So let me get my notebook because I wrote down some notes on this and we'll kind of work off that. Wait a minute, my notebook isn't here. Let me get it. 1 second. Got it. Okay. Yeah, fair enough. Okay, so let me go ahead and grab this color quantization. Opened up to the exact right page, saving a little bit of time there. Not really that much, because I have to figure out where to put it on my desk anyway. Okay. All the time, how... What? I'm not... I mean, he's definitely bothering to read your text messages, Frank. I mean, anyway, so... What are we going to do? That's a second warning. Okay, here's what we're going to do. We're going to be using a particular directory known as cimage.h. That's what I want to be using for this, just because I have it installed and it's pretty useful. So let me first go online and let me see what we got here. Let's go to images. So let's go to Google Images. And I mean, he'll be back tomorrow. Hey, that's your fan. What's up? Let me just Google Images. Here's a flower wallpaper. Let's just grab that. How about what do you guys want? Animals, spring flowers. I just need to get an image that we're going to well, butcher basically. What we need to do is take an image to quantize the color on, right? And again, guys, we're basically taking an image here and just reading in all the pixels and then changing the color. And if you guys have an idea of what picture you want, let me know. Right now I'm just gonna take, I don't know, spring flowers. I feel like, what is computer coloring? It's basically how we represent the colors in a way that kind of saves the number of colors that we're representing, if that makes sense. So we represent the smallest number of colors possible. Let's do a purple flower. This one looks like it's pretty good. This one, right here. Yeah, that looks like a pretty high resolution image. Frank, come on. So let's go ahead and view image. This is the image I'm taking for now. Save image as, and let's go into, where am I? How about recently used? Probably have Simuleos in there. Of course I don't. So let's go to Simuleos. Color quantization. Here we are. And then we're going to save it as flower power dot JPG. No, I would like to use a PNG just because I I might have Zadiston. I searched Google Images and then yes, so that's exactly what we're doing, that your fan. It is basically taking a colored image, reading it in pixel by pixel, and then changing each of those pixels to match a defined color palette. And that's all we got to do. And honestly, it should be super straightforward. We'll see how far we get. So let's go here. Let me do an ls. And now let's just modify some things real quick, just so we have the notation correct. So let's go into color quantization.h. Okay, so what do we have here? We're going to have to read in another guy here. So let's go ahead and read in. Include cimage image.h. And you know what, guys? I failed miserably at something starting this out. Let me do make. Oh, good. I was so worried that in order to read in cimage, I was going to need some sort of library or something like that I was going to have to read in with it. And I just completely forgot to look that up beforehand. I usually try to look that kind of stuff up so I don't run into an issue, but because honestly, guys, for some reason, I don't know why, but setting up the make command is usually like the most annoying challenge to work with. TWDWD, we are doing basic color quantization. It's, we don't have Visual Studio. So that's how it is. So let's go down here. What do we want to do? So we have our struct particle. However, in this case, we can remove some of the unnecessary stuff. So let's go ahead and see. We need vector position, but in this case, vector position is going to be a color of RGB, right? So let's go ahead and remove the stuff we don't need, which is going to be previous position, previous velocity, acceleration. Don't need any of that. Mass. Do we need a mass? Yeah, we need a mass. And let's see what we want. It is kind of the terminal version of Visual Studio. Okay, radius. We don't need a radius in this case. All we need is vector position, mass. However, we do need a center of mass. So let's see, vector. Oh, but is that in particle or is that in node? It is in node. Here we are, particle center of mass. Good. Okay, so we're going to keep the same struct particle. I see no reason to change that. And let's go ahead and change vec v, vec a, and all that kind of stuff. So let's go ahead and remove these guys. And let's go down here and remove these guys. Oh, we needed mass. And radius, of course, is not going to be here either. Yeah. I don't know. I mean, here's the thing, guys. I always get so sad when people bring up Einstein. I mean, I know he's like he's super smart and stuff. I just feel bad about myself because I just don't know. I don't understand everything that he's done. You know, like, as a physicist, you'd think, oh, sure, I know everything about Einstein, but I just don't. Like, there's so many just things that he has said that I have no earthly idea about. So let's go ahead and remove this guy too. Okay, and for this, we're going to change particle mass to just 1. The idea here is that we're just going to count the number of particles that we have so that we can more easily take into account the center of mass. Turning off the air conditioning, and let's keep going. So, now struct node, what do we need here? We need position, box length, parent, all that's necessary. Children, necessary. Particle center of mass, again, necessary. Vector pvec, all this looks good. So node isn't going to change. However, we are going to remove a few of these guys down here. Feynman is one of those guys that, like, I actually know more about Feynman than I do about Einstein stuff. Just because I'm a little bit closer to Feynman stuff. That said, I don't understand Feynman diagrams to save my life. Like, it's just... like, if you guys have ever seen Feynman diagrams, it is just... they're crazy. I don't understand them. And if you understand them, maybe you could do a... you could stream in hashtag physics for a little bit and do a video on Feynman diagrams. In fact, I've been thinking about it a lot, guys. What would you guys say if we, let me see, traverse post order, that's all necessary. Force to integrate, not needed. If we, how do I put this? I said journal club before, but maybe we don't need a journal club. Maybe we need something more like, I just do some weird random thing that you guys probably haven't seen before in physics, you know, like maybe we learn Feynman diagrams together or something like that. I don't know, just something, you know. Function will be used later to plot out what particles actually see with the Barnstad algorithm. Let me see. We can just keep the particle output the same. Now let's go into color quantization. .cpp. I don't know, I just thought it'd be kind of nice to learn about some stuff that I just don't know about. Okay, traverse post order, what is this doing? This is going through all of our number of steps. However, quantum chromodynamics, holy crap. Maybe that was bad. Maybe I shouldn't have said that. I know what the diagram is. You do? Okay, well, you're better than I am then. Okay, so what do we have here? Let's go through main and let's take a step one by one. First of all, we have int num steps. This is basically the number of time steps we go through. However, in this case, we don't necessarily need to worry about this. Because what we're going to do is we're basically going to read all of the pixels into a vector, which is, well, one second. It's 4 arrow lines and squiggly line connecting them. Yeah, that's exactly what it is. One of the many Feynman diagrams. The thing that gets me is always when you have these disconnected diagrams. Like you have one line that goes up and another, and then there's like a circle up here and they're just not connected at all. And I'm like, I can't for the life of me figure it out. You know, if it's something simple, sometimes I can kind of wave my hand at it and figure it out, but I don't know, guys. Okay, so what do we not need for this? Well, again, we're only reading in one image, so we're not going to need to do different time steps, so far as I'm aware right now. So you can go ahead and remove that. Let me see, num steps, int octree string 2 data I. Yeah, so I think we're only going to need one octree. So let's go ahead and, let's say we remove this line, octree files, in place back, this line, that line. Where's our octree files? Here. And then we're going to say, let me see, upstream, same like what we did before. So let's go ahead and yank this guy, paste this guy, and we're going to say, what do we have here? Let's see, so we have everything now. Octree output, octree files, I, good. So we're going to call this octree output. Oops, sorry about that. Oh, output.
But out of curiosity, have you guys
Have you guys played the Rocket League for Linux? I don't know if you guys have or have not. I went to the streaming section for Rocket League, and I looked for people who were streaming on Linux yesterday afternoon, which may have just been a bad time. And there was like one guy who had like 4 viewers, and I'm like, oh, that kind of put me in my place. I was like, man, I guess I didn't realize how few people care about Linux in the actual gaming community. Let's see, because it's the only game that it's the only community I'm actually a part of. It's kind of one of those things that, I don't know, I felt like everyone was excited for Linux on gaming, or gaming on Linux, but I guess maybe I wasn't quite right about that. Okay, so let's see. What do we have from here? Let's do velocity square root, we don't need that. DT, don't need that. Particle pvec. These are all testing, so we could probably remove all these guys. Okay, now we have pvec 0 previous p. Don't need that either. Print pvec 0 previous p. Let's just print p. Okay. So what we need to do here is, let's see, make Octree here. Good. So let's do one thing here. Reading in. Yeah, I'm about the same, Gustorn. It's just, is it bigger than Mac? That's your fan? I didn't know that. I mean, that said, kind of makes sense in a bit, in a weird way. Okay, so let's see. Creating Octree reading by, 1 second, reading pixels. To come later. Okay, and what time I do? I'd rather spend doing something else. Yeah, I get the same feeling. You know, like it's cool and all. Like, don't get me wrong. If this was any other, how do I put this? Like, for some reason, I can't find it fun anymore. Like, it's just like, if I want to do something, I would, okay, I'd do something else. Sorry about that, guys. Okay. So what do I want to do? I think I can remove this entire loop. Make Octree. Gosh darn it, I have something in my throat, and it is driving me nuts. Okay. So now we do, let's see, particle output should be okay. We can leave that the same. Sorry for the yawn. Okay. What do we have? SVC out, P out. Never played games on Linux, but I hear Wine's gotten a lot better. Actually, yeah, it has. In fact, the other day, there was this game dev on Twitch here whose Linux version of his game wasn't working, so I just kind of played the game on Wine, and it was working quite well. In fact, for a lot of big games like Guild Wars 2 or something like that, I'll use Wine for that. And in fact, I do play Guild Wars 2 semi-regularly. I played it about 3 weeks ago. So that's, and Rocket League I played for about, I'd say about an hour maybe, yesterday. I played it just before work. And just after work, but I'm just so bad at it. It's just not, it's not my game, but that's okay. DD here. DD there, remove some force integrate flags, or whatever they're called. Oops. Particle output. Gosh darn it. I did it again. Octree output. I don't know why we're outputting so much particle data. So let's go ahead and remove, let's say these guys. That should be okay. Oh, really? Do you like Osu? It's one of those games that I enjoy. Osu. It's one of those games that I kind of enjoy watching. Let's see. Divide Octree, make Octree, create random distribution. We'll leave that all there. That username though. I really used to like playing games, but nowadays I'd rather read. Yeah, I think it's just I'm kind of the same way, Gustor, and I've been kind of really relaxed when it comes to gaming lately. Let me see. Where are we? That your fan. But better and better. I watched Pro Turning of RL, and holy, wait, what is RL? Real RL is the only thing I can think of. Real life? Are you saying Pro Tourneys as in like the Olympics of real life? I'm kind of confused. Fair enough. So let's do Octree output. I didn't know you played a lot of League of Legends, Tiddly. So let's see. What do we have here? I feel like most people who watch this stream are kind of growing old. You know, they don't quite want to get rid of their gaming streak, but at the same time, like, they definitely, I don't know. I just feel like that's kind of the people I would attract here. 1 second. We need to remove all this RK4 stuff because it's no longer necessary. So let's go ahead and get rid of it. So RK search. Yeah, let's just get rid of it. Do you feel comfortable with the black and white text editor over an IDE? Of course I do. Let's remove this guy. Removing Verlet. And I'm very, we might stick to Verlet at the end for the main series stuff, just because the Verlet algorithm is a little bit quicker. And Mindaugus, just to fully answer your question, this is how I learned to code, and so I've never had to use an IDE, and I've never seen. That said, I see the advantages to using IDEs, especially when it comes to debugging. However, I'm in the wrong file. However, I can't really use an IDE at work, and so it's kind of like, well, this is just how I code now. So I haven't really. Okay, looks like I missed something. Let me go through and let me check this up. No matching call for particle, vec. So let me go into vi color quantization dot h. Oh, my bad. Color quantization dot h, and let me see. So I fixed everything in here. However, I didn't fix everything over here. So let me check where the issue is. It is in 57. Oh, 57. 1 second. Color quantization dot h 57. vi color quantization dot h. Go to line 57. Here we are here, and we need to remove this guy here. Good. And then we need to remove these guys here. Let me see. What do we have here? I still play games. Recently I kind of swapped homework first, and it's all right, really. Fair enough. Let me see. I really like reading when I was little as well. I have a ridiculous number of books, but as I had less and less time reading one out. Yeah, fair enough. There's no clear line between IDE and editor nowadays. What's Adam supposed to be? Yeah, I guess it's fair enough. Yeah, honestly, that's the thing. Like with OSU and with games like that, it's you can honestly see yourself becoming better. And honestly, that's why I like doing programming here too, because it's one of those things that, yeah, sure, it's slow progress at times, but I definitely see myself advancing as a programmer. I definitely see myself getting better. And that's kind of nice, you know. There's very few other things in real life that I can do that I can honestly see myself improving at every time I do it. And that, I don't know, it's just neat. So let's go here and let's make. Okay, we got some more errors. That's okay. Let's go and fix those up. 57. Did I forget to write? Or maybe I just forgot to clear. Oh, yeah. Okay. pvec was not declared in this scope. Fair enough. So let's go to line 28 there. Let's go to color quantization.cpp. 1 second. And let's just create a whole bunch of random particles for now. Let's go over here, make that. Gonna be a whole bunch more errors. Sorry about that. This guy's clear. There might be a Japanese word for that. I'm not sure what it is. Let me see. So it looks like we have fewer errors here. Error output was not declared in this scope. That's because I named it O output. Let's rename it output. And now let's see, what do we have here? pvec acceleration. Of course there is no acceleration. Let's go to where we have the acceleration. Here. Force integrate. We don't have anymore. So let's go ahead and just remove this entire function. Now let's go ahead and clear a couple times. Yeah, I know we can use Control L. And let's make that. And what's the issues now? So new allocator color quantization 34. Getting particle vec whatever. 1 second. Color quantization.cpp 15. Oh. Color quantization.h 34. vi color quantization.h, and let's go to 34. Here we're at particle, double, mass. 1 second, what am I looking for? Double mass, that seems fine to me. Let me see. Sundoku, I see. Let me see. I vaguely remember there being a Japanese word, yada yada. It's many things what an ID provides. JetBrains really does a good job. Really doing a good job in IDs. I've heard a lot about JetBrains. I think some of my friends use it. So let me see, what do we have here? Color quantization 33. Candidate expects 0 arguments, provided 4. 1 second, something happened here. Candidate, particle. Particle vec double. Candidate expects 2 arguments, 4 provided. 34. Oh, what did I do wrong here? Let me see. Can expect 0 arguments for provided. Color quantization 29. I don't know what it's pointing me to, but I think the issue here is over here. So let me go to CPP. And let me see. Let me see if we just find particle. Here. There. There's all fine. I probably define something in here. Do I not? Oh, here's probably it. Let's see. Box distribution, generation. Yes, so that's all we need, but we need to remove these guys here. Let's make that. Give it a second. Okay, that one ran. Seems to actually run perfectly okay. So now let me go ahead and ls here. Let me go ahead and do a make clean. Now let's do a make. Okay, give it a second to do its thing. Now let's go into vi octree 0.dat. Good. So we have our octree being created exactly as we might expect. So let's go through and check that out. So what I want to do is, one second, I need to think. I want to do new plot, qplot minus. Here we have our octree. However, the octree is super duper big and the particle is super duper small. So let's make the octree of the appropriate size, which will be from 0 to 1. And let's go here, Control D, and make that guy. Now we're going to do new plot, qplot. And we only have one particle in it right now. That's my bad. Let's go up here and change the random distribution to 10. I think I did the opposite of what I needed to do. Let me check this again. One second. Let's do new plot. Oh no, this is right. So here is our octree code. It works pretty well. Now we just have to modify it for colors. And honestly, guys, I know it seems like we're moving slow, but this is literally all we need to do. It's not much more than this. Yeah, someone mentioned finished that and Snow Crash a while back. Yeah, so I think you guys were talking about Neuromancer the other day on the channel. I mean, Culture Series. The weekend due to the back library. Oh, by the way, guys, in terms of books, has anyone here, I know this is kind of a weird book series to recommend, but has anyone here ever read The Wheel of Time? You know, Eye of the World, The Great Hunt, all of those books. Because honestly, those books, like that was my childhood, those books. I loved those books. They were fantastic. And it finished a few years ago, but man, it is such a good book series. Good, so this seems to work okay. I was just curious if anyone ever read it. I said Power Red first half of Sunday. I don't know what that word is, but that's okay. Had a little trouble getting the Culture Series. Maybe I'll explain. I'll try again sometime in the future. So the series is huge. It's like 14 books long, and each book is like 600 to 1,000 pages long. It's an incredibly long series, but I don't know. I loved it. It was one of those series that I genuinely enjoyed the whole way through. I could just absorb myself into the book, or the book absorbed me into it. I don't know exactly what phrase I'm trying to go with there, but it just, I don't know, I liked it. Okay, so we have everything being output. Now there's one thing to point out. This particle output that's going to see out is not doing anything. Let me just go ahead and I'll leave it up. That is true though, the middle part, so around book 8, for example, book 8 was kind of slow. I think The Winter's Heart was the one that really struck me as a slow book. Or it wasn't really slow, I just wasn't engaged in the plot of Perrin, who was one of the main characters. Okay, so let's go through and let's get this done. Maybe consider Flevis as just a bad starting point. Oh, okay, so what do we need to do? We need to create a couple different functions here to basically read in the particle data, or the, what am I saying here? Read in the image data. So what am I going to do? I'm going to basically create a function for that. So let's go over here. Let's go into color quantization. .h. Oh, that was a /h. Oh my gosh, what am I doing with my life? .h. And let's go down here and let's add in the appropriate. What? The heck? One second. What am I doing? What? Okay, let me quit this. I'm sorry. I don't know what I just did. Apparently pressing space and J. I don't like syntax highlighting very much. It kind of drives me a little bit nuts. I understand that it's kind of annoying for a lot of viewers. And I've considered adding it in for this channel, and I did on one stream, but I I couldn't do it. It just wasn't my thing. Okay, so let's go down here and let's go ahead and add in the appropriate function. So we have particle output up here. Let me see, where is the create random distribution? Here it is. So here's what we're going to say. We're going to say function. One second, misspelled function. I spelled it as function. Function to create particle data. Data from image colors. So what we're going to say is the following, and it's just going to be, I hear that syntax. Actually, there was a, how do I put it? We got a steering wheel cover for someone, I don't remember who, but we got a steering wheel cover. And on the tag, it said cancerous in the state of, cancerous in the state of California. So it's only cancerous in the state of California. I'm not sure why. Although I think it meant that it was considered cancerous by someone in the state of California. I'm not sure. What am I doing specifically? So JA2Y. What I'm doing here is I'm taking a whole bunch of particle data. So this particle data is going to be read in from a file as RGB. You could imagine RG and B to be the X, Y, and Z axes, right? So we're reading in the RGB as X, Y, and Z axes, and then we're basically splitting them all up into a whole bunch of little boxes. After splitting them up into a whole bunch of little boxes, we're then going to basically take all the colors, squash them into the same color, and quantize them so that we use less colors for a very high resolution image. So the idea is that if we have a whole bunch of colors, we use fewer colors for the quantized version. And basically that's what we're doing. We're taking a whole bunch of colors and quantizing them. Reason being that it's just a good application to Octrees, and it's a good introduction to what they are. And that's kind of the idea from there. So I can show you that in just a second if you stick around while I write this function, and we can work on it there. Thanks for coming in, man. So what do we see here? Function to create particle data from image colors. So let's call it std vector. And how about we call it of particle 2? Hopefully this will work out. And then we want to do create, what do I want to say? Particle data. How about we just call it image read? Something like that. And what do we need to read in? Well, basically the only thing we need to read in is an std string. That was stdd string of, what do we want? We want, 1 second. Oh, obviously image. Well, that was easy enough. We're done. Okay, so now let's go down here and let's add in the function. I'm going to put it right under create random distribution because they serve a similar purpose. So let's put this here and there and remove this, add that. Good, and let's do it. So we have CImage being read in. So let's just go ahead and do what we need to do. So we're going to say CImage of floats. And let me see. We have image of image. Well, maybe that was a poor naming convention on my part, but that's okay. So CImage of floats. Then we say, let's see. CImage display main display. Float pixel value R image. Okay, so now we need to basically go through here. I'm not sure what this next bit does, I'll be honest. So let me go up here and let me change the name of something. So let's say image, image file. Go down here, image, what did I just do? There we go, image file. 1 second, file. Here we go there. And let's go over here and change this to image file just to save the same thing. Okay, so now we're going to go down here. We have image file there. The next thing I wrote down to put down, though I'm not sure if this is necessary, is the following. CImage display, if I can spell display. And then we want to say main display. Again, I'm not sure if this is necessary. We might be able to take it out, but I'm going to put it in for now. Image. Okay, so now let's go up here and let's create, let's see, std vector of particles. And what do I want to do? I basically want to make this of a particular size. So I need it to be of the size of the number of particles we currently have. if that makes sense. So we have our particle, and we need to go through, like, if we have a whole bunch of like pixels, we need to go through all the pixels. Let's see, I've missed a lot of chat. Let me see. Let's see, KDX slow, not at all. Maybe if you work on a notebook or something. Not really a fan of Eclipse. PHP Storm by JetBrains works faster over Sublime, though. Oh, interesting. Let me see. In fact, yes, I do work on a notebook and bookmarked. Good. So, I'm glad you guys are enjoying the chat. Feel free to, again, talk about whatever. This chat's pretty relaxed. 6 o'clock in the morning, that means we're halfway through. Still got a lot left to do, though. We're basically just getting started. So vector particle, and let's call it color. Plural. That might not be the best way to name this. Let's say colors. Now, what size are these colors? I'm not sure what image has within it. I'm not sure how big image is. And I feel like... Here, let's go through here. And let me just try something. So let's do... Down here, let's just do... let me see. Surely there's a way to iterate through this. So let's do a SCD, vector, and let's just make it of a particular size. So let's say vector of particle. And we're going to make it color data. Why not? And we're going to make it of size, and I don't know if we're allowed to do this, image.size. I don't know if this function is in there. So let me go ahead and write quit. Let's make this. It's going to give us a bit of an error. Let me see. CImage was not declared in this scope. That's because we're going to have to do... and guys, I know you guys are not going to like this, but I'm going to do it this way. So we're going to say using namespace CImage library. Of course, we don't have to do it this way, but make... it kind of helps a little bit. Okay, let me see here. We have a whole bunch of errors, and it's probably because of that CImage.size. Let me see. No matching function called CImage library. CImage... what? Is that because I forgot? No, we have float in there. Image hills.png. For CImage library, float... Oh, maybe it needs to be .cstring? Maybe that's the issue. Let's try that. .cstring. Make. Let's see what we have here. Return statement and function returning non-void. Okay, that one actually worked. Don't know why, but it worked. Okay, so let's go down and let's see what we have from there. So now we have all the particle sizes here. And let me just, for my own sake, let me do std cout. Let me see, image.size, just so that I know what we're outputting here. Image.size. And let me just, new line here. And let's do return. What do I want here? Color data. Okay. So let's also put a quick statement in here saying, what do I want to say? Number of pixels R number is. There we go. Now, what do I want to do? I want to go up here, and instead of doing pvec here, I want to do the following. So we're going to say, actually, let's yank this and paste it. X, and let's do pvec, and it's not going to be equal to create random distribution anymore. Now it's going to be equal to image read. If I can spell that right. Read, and then we just read in the appropriate file name, which, if I remember correctly, is flowerpower.jpg. Now, I don't know if this is going to work or not, but we'll see what happens. Write this, go over here, and let's make it. Is it working? Okay, something happened. I'm not sure what that was. And I'm not really sure what's happening right now. So let me control C here. And let's do the following. Let me do makefile. And let's remove this dev null thing here. Gonna go here. And I'm also going to remove the particle output std cout. And I guess those extra lines right there aren't necessary here. Let's make that. Okay, let's see what happens. Give it a second. So we have some problems here. 1 second. you can do CT character to change the text until the first occurrence of character. Oh, that's pretty neat. Go ready to change stuff until the semicolon, for example. Yeah, that is quite useful. Let me see, what happened here? Time, command not found. Oh yeah, we're running into the same issue as before. Let me just go here and let me just run /color quantization. I don't remember why, but we had that issue before. Now let's make that. Make clean, make. Give it a second. Let me see what happens. Okay, if you saw that, something happened. I'm not exactly sure what happened, but something definitely happened. So I think that's because of the CImage display, which I don't care about right now. So let me just go ahead and remove that line, and let's see if this works. Make. Again, guys, this is the first time I've been using the CImage library, so I'm not exactly sure what it's doing here. Like, why it's taking so long in here. I just don't know. I don't know if it's hanging, if I need to quit it. I'm just really not sure, because we've already read in the particles, right? So let me go ahead and Control C and let me see what we have. LS. We have Octree 0.dat. It looks like everything should be good. Let me output something over here. Let me do SCD, cout, finished. End line. Let's go over here and make that. Give it a second. Okay, so clearly we're not going through everything. So clearly something's broken. I'm not sure what it is though. So let's see, what do I want to do? I want to... I'm not sure what's broken here. So let's see, where do we get to? We probably get to number of pixels here. Return color data. Is it in the particle output? Let's just comment this guy out. Comment this guy out. Comment that guy out. Let's go over here, let's make it. Because we clearly output one... No, we don't. What are we outputting? What is this 0, 0, 0? Return color data. Should be okay. Number of pixels is, sure. What else are we outputting? Image read, print. Oh, it's the print function there. Let's go up there. Comment that guy out. Write this, go over here. Let's make that. Okay, so I think... Number of pixels, root node make Octree. Oh, maybe it's in the, I don't know, guys. I don't know where this is. Let's just remove everything. Go into color quantization.p. Let me make it. Something is causing it to hang, and I think there's like some sort of weird infinite recursion. Okay, so there's probably, I think I figured it out, some sort of infinite recursion in this make Octree command. So once we get the color data in, it shouldn't be an issue. Now, what are we gonna do? Well, let's go through, and let's just, well, read in what we need to read in. So this is going to be the red, green, and blue data for each of the pixels. So we have a vector of particles here, and let's just go through all of the pixels and read them in. Yep, that's exactly what we need to do. So we're going to do for int I equals 0, I less than, I guess we're going to do image dot size, and then we're going to do plus plus I. Go down. What did I miss? Anything? Let me see. Or you have an ID who refactors everything for you, since you spend those 10 seconds loading all projects into RAM and indexing. Okay, so we're going to do this. Now we go down. What do I want to do next? I'm basically going to go through and turn all the RGB data into a position to put into our PVEC. Now let me check and see what else PVEC has. So let me see. VI. What do I want to do? Let's do color quantization.h. Why do I always put a slash? For some reason my hands are like, holy crap, slightly off today. There we go. So what's in position? We have mass and we have vector p. So all we need to do is the following. We read in the vector position and go from there. So we're going to say color data of I dot I guess is going to be equal to particle of, what do we want here? I guess we're going to say vec of the following. So we're going to say vec of this is going to be kind of weird, So let me go up here and let me define some things. So we're going to say float, because that's the only thing we're allowed to use here, float. And we're going to say R, G, and B. I suppose it could be lowercase. R, G, B, semicolon, remove that, add there. Good. So now we're going to say of, go up here, and we're going to define what R, G, and B are. So we're going to say R is going to be equal to pixel val. I think that's a capital P, or maybe it's a lowercase. Pixel val. The one ID that has distant Vim emulation is Visual Studio. And I'll be honest. Yeah, fair enough. So pixel val. Oh, I see. Sorry about that. Image of, let's say we have I, and then we have J. Sorry, this is kind of rough. Let me get through this. And then we're going to say 0, 0 for red, and then we're just going to basically do the same thing for blue and green. Paste. And so we're going to say blue, we're going to say green, and we change this last number here. So 1 is going to be blue, and 2 is going to be green. Now, one thing I have to do is add in a J loop. So we're going to say for int. Oh, wait a minute. Shoot, I have to think now. Hey, Ginfira, what's up? So int J equals 0. Let me see. J is less than... I don't actually know how to find the pixel length here, or pixel width or whatever. So let me see. C image. C image. Then we want image height. Let me see how to get pixel data stored in C image. Maybe this helps. I just want to see how to get RGB value. That's fair enough. Hey Zuki, what's up? Haven't seen you in a bit. Or maybe I have and I just forgot. Sorry about that. But how have you been? So what do we see? Width height equals source width. Oh, fair enough. Width and height. Let's do it. So image.width. And then we go image.height. Here. And then we do ++i. And I might change this in just a second to do something a little bit different, but that's okay. Let's go here, and then we want RGB, and then we want to read in 1. And that should do it, I think. What do you see? I'm fantastic, Zuki. Thanks for thanks for asking. So let's go here and let's add in a couple spaces here, and of course here and here. Oh no! Shoot! That wasn't what I meant to do. I thought I pressed capital I, but I pressed lowercase I. Vim struggles. Oh my gosh, that was the I struggles. Holy crap, what am I doing? Undo that one. Yank this. Paste that. Change this to green. Go over here, change this to a 1. Go over here. 1, 2, 3, 4. There we go. Red, green, blue. Done. Sorry about that. Let me see. Yeah, there's one for Windows that takes the command line tools and makes everything 75% longer for no apparent reason. Huh. Haven't had time to watch. Been getting ready for university. Ah, man, that sounds fun. Well, in a way, fun. I mean, you know what I mean. I don't know. I found that my undergraduate time was actually super fun. I didn't like it at the time, but now looking back, I'm like, oh yeah, sure, I had friends then. Yeah. Okay, so color data of I. So here's the thing, guys. We are currently saving this as a vector of particles, right? One thing that I would like to have outside of this particular function is the, what do I want here? Is the image height and image width. So what I'm thinking about doing here is reading in the image to the image read function. So let's go up here and let's initialize everything in main. So we have pvec here, and let's go down here and say reading in image from cimage.h. Okay. I haven't been watching how many viewers there are lately, but currently have 30. Oh, wow, that's quite nice. Okay, so let's go through here. And let's see, what do I want to do here? I want to grab these guys here, and I want to go up here and put it up there. You don't have to be a freshman to like school. I mean, come on. So what do we have here? See image float image file dot c string. Seems fair enough. An image file is going to be defined up here. So let's go down here and, or let's say std string image file. And we're going to say this is going to be equal to our flower power image. Flower power dot png. Oh, JPG, I think is what it was. Good, let's put in, oh my gosh, the appropriate guy there and the appropriate guy here. What do we have here? Can you merge tree and git merge and terminal? Can you see? There is a way to do that, but I don't remember exactly how to do it. I know there's a way to visualize it though. Sorry about that. I just can't seem to remember right now. So we don't need to do see image display, vector particle color data image size. Let's leave this one out. Number of pixels is, we'll leave that one in. Now let's go down here and let's modify the function a little bit. So what we need to do is remove this guy, and that guy. Good. And now we're going to read in the appropriate image. So we're going to read in the image file and the image itself, which I'm going to read in here. So what is the type of the image? That's a good question. It is see image float. So let's go down here and add that in. See image float. Hopefully we'll be able to read this in no problem. See image of float. There we go. And I'm going to say image. Good. The staff is a joke. Freshman first year. You wouldn't be looking for GUI if you were on Linux. There are good IDEs on Linux. Don't get me wrong. I'm not saying there aren't. I'm just saying I don't use an IDE, you know? Let me see. What are we doing? Image read. Let's go ahead and read in the image over here too. So let's do see image float image. There we go. Right quit here. Now, what do we need to do next? We have all this stuff and RGB. I think if we write this and we make it, it's gonna break. Yeah, I should have figured that. Okay. Error, primary expression before float. Okay, let me see. Color quantization H. This is probably because we're not using the namespace over there. Let's go over there and let's check. So color, one second, quantization.h. And let's go down here and let's do using namespace like we have up here. Using namespace C image library here. And let's put it over here. And now I would imagine, though I'm not sure, if we remove this space over here, remove this line, write this, go over here, right quit and make that, we shouldn't get the same error we had before. Let me see. Where are we? We are right here. In function int main cannot convert constant character star to C image library. Oh, that's because I screwed up on the image read. My bad, guys. Let's go here to image. God, Genfuro. Okay, let me see. Honestly, come on. It's one of those things. Let's go ahead and clear the terminal a little bit. I don't know. Depending on what you're studying, though, college can be a lot of fun. Clear, clear. Make it one more time. Now let's see where it breaks. C image library cannot convert constant char. Didn't I just fix that? I must have forgotten to write. Let's try making it one more time. Okay, error. Image is not a type. C float image. Let me see. Color data. C float image. Color quantization.cpp 79. Let's go there. 79. What did I write down? Color data. C image float image. Oh, oops. This needs to go here. It's my bad, guys. I don't know what I was thinking. Let's remove this. Write this, go over here, and let's make that. I'm from Belgium, though, and 18. I think it's about 18 for most people. Oh, good. That one actually worked. Getting there, guys. And guys, as I said before, this should be a relatively trivial thing to do. And by trivial, I mean the physicist's use of the word trivial. 18's about right. Game development seems actually super fun. My cousin actually studied game development, and he enjoyed his time there a lot. So what I want to do now, what I want to do is I want to output something here. So I want to make sure all the color data is being read in appropriately. So let me do this. I'm going to do print color data of I, which should be particle data, so this should be allowed. Oh, I'm sorry. Dot P. Let's go here. Make that. Give it a second. It's doing something. Ah, there we go. All the data. Okay, so it is out of 255, apparently. Which is good to know. So what we need to do then is scale this. They look like they're all floats, so that's good. So we should probably scale it between 0 and 1. Right? Sure, why not? As long as you study real science, it's fun. I wouldn't want to study women's studies or gender studies. Well, you know, the way I see it, at least in the US, you can do a major and a minor. Most people major in something that they know will make them money, some sort of science or engineering degree, and they minor in something that they want to study, which could be women's studies or art or something like that. We are creating images, we're reading in images, and then we're going to basically make the color worse. We're basically doing something known as color quantization, which you can look up online if you want, but the idea is that we're taking the full spectrum of colors, and we're going to basically all the colors that are red, we're going to approximate as the most common red that is available there. Why float for color? It's an RGB value, right? So we have red, green, blue. So that's what the color is defined as. In this case, just because this is how we currently have it defined. And in fact, R is going to be our x-axis, green is going to be our y-axis, and blue is going to be our z-axis. And I'll show that to you in just a second. I just need to go through and get all this data in. So let's see, what do I need to do to convert this into what I want it to be? I guess we just say R is going to be equal to this, divided by 255. Divided by 255. Oh, I keep missing the period for some reason today. And then go over here and we say 255. Here we go. Write this, go over here, write and quit. Why did I write and quit in a terminal? Make it again. Just checking to make sure that we have the data between 0 and 1, which it should be. I see no reason why it wouldn't be. Good, it's between 0 and 1. Now, just for the record, the image that we're looking at is this one. So there's a whole bunch of white in it. So forgive me that I chose an image with a bunch of white already in it. Okay, so now we have all the color data. We can actually create an Octree from this. So what do I want to do? Where do we do the Octree? Where's the Octree? Octree is here. Now, because this is between 0 and 1, what I might also want to do just to kind of get everything, you know, in the mood is subtract to 0.5. Because nothing gets you in the mood more than subtracting half of yourself. Okay, let's go ahead and subtract a 0.5 here. And I forgot a 0 is up here. Yeah, we can use our imagination, or I could just add in a 0 and a 0 there. You should really write 0.0f. Let me see. They're doubles. Or D. Let me see. I mean, aren't colors always whole numbers or as integers? I'm not sure. Aren't colors always whole numbers as an integer? I'm not sure. I'm not sure exactly what we mean here. So let me go up here. What's wrong with the notation? Let me just, if I add zeros, does that help? 1 second. Let me just make sure this works with what we currently have, and then we can worry about fixing everything else up from there. No, the colors are definitely not integers. Oh, wait. You hate leaving the zeros? Okay, so if I add the zeros in, is that okay? So let me go ahead and remove this, remove that, divide Octree. Okay. And then we want to do Octree output down here. Okay, we have particle output up here, and let's see what happens if we run all this. Hopefully it'll work. Let's make it. And this should hopefully answer your question, the staff is a joke. So here we have all this. We should be creating the Octree now, I think. The colors were, yeah, I guess you're right. They were from 0 to 255. But then we want to put them between 0 and 1. Depending on the color space, deep down, the monitor can only display RGB values, but have a look at HSL, HSD, and other color spaces where you deal with angles, alpha. Yeah. I've actually never seen that one. and colors numbers between 0 and 1. Okay, 1 second. I've got a feeling this is too many pixels. That might be a bit of a limitation here. Let me see. Can we parallelize this in any way? How many pixels did we read in? We didn't read in that many. We only read in... oh, like 17,000 or something like that. Apple does not use RGB anywhere, though. Maybe not. Okay, so let's go down here. Let's remove the print command here. And I guess we'll just give this guy a little bit of time to run. While it's running, I'm going to get a quick sip of water. Because I don't currently know what is happening. Let me see. It could be. Let me go ahead and right quit here. And let me do an ls. Qplot Octree 0 via Octree 0.dat. There's nothing in Octree 0.dat. Vi pout.dat. Nothing pout.dat. What are you doing? Control C. Oh, it's probably generating the Octree. That's probably what's happening right now. Let me see. Why would it be taking so long? So let's go here, Control C. I don't know what's taking so long, so let's go into color quantization.cpp, and let's go down to the make Octree command. We're reading in the Octree data. Let's go make Octree here and there. Okay, so what are we doing here? It's basically recursively going through pvec p position. You know, we might not need. Oh, maybe we do. Divide Octree. What do we have here? New node, pvec.reserve. So this is us just making the Octree, putting it in its places. So let me see what's actually taking so long. So we're gonna go up here to main, and let's go down, make Octree here. Let me just output something. So we're gonna do std. See out. And what do I want to see out? I want to see out making Octree. Okay. New line. And let's go down here to std, see out. Dividing Octree. 1 second. Octree. And here's what I'm going to do, guys. Just because this is taking a while and we are on stream, I'm going to open up the file that we're working with in GIMP real quick. So GIMP flower. 1 second. flowerpower.jpg, and I'm going to basically cut this a little bit. So let's do Windows, Toolbox, and let's just make this a little bit smaller. So let's grab some region, like let's say here, or something like that. Close that. I don't know how big this is, but that's much smaller. So let's do File, Export as Flower Power. Let's say, I don't know, we're going to save it as a PNG, and we'll save it to .png. Export, export, close. Discard changes. Now let's do where we put flower power. Let's change it to flowerpower2.png. .png. That was an O. There we go. Now let's go ahead and make that, and hopefully we'll be able to get through everything a little bit quicker. Let me see. Number of pixels is still 27,876. That's a big number. However, we got through it. So let me do, let me see, the last new plot should do it. Okay, here's our Octree. Okay. Well, this is slow and laggy. Let's cut the image down even further. So let's do, I guess none of the non-natives like the 0.5 idea, leaving out the leading zeros. No, I usually have the zeros out too. I smell a low-key roast. Not sure where that came from. Okay, so let's go ahead here. And let's open up the image one more time with GIMP. Let's see, how big is it? It is, oh, that's Flower Power 1. I want Flower Power 2. There we go. How big is this image? This image is about 100 by 100 pixels. How many spaces did I say we have here? So let's just make it even smaller just for now, just again, because this is just for debugging. It should be okay. So toolbox here. And let's just take this region right here. So we'll take a 50 by 50 image. There we go. Let's crop that. file, and let's do export as. Same thing, export, replace, export. Now 50 by 50 should give us a 25,000. Yes, that's exactly what the point is, to reduce the image size. So let's go ahead and discard changes, close this. Now let's do it one more time. A new, ooh, that was not what I meant to do. Okay, so now we're gonna do Control D, and let's do make clean, make. Okay, so let's check the number of, 1 second, 7,500. Is that right? 50 by 50. Shouldn't be 7,500. Oh, maybe. Okay, so let's do here. Does it reduce the size or only after compression? We'll show you in just a second. So let me do the last new plot. Okay, so here we have a whole bunch of data. However, it's I'm not sure I appreciate this data. There's something weird that's going on. Okay, so here's our Octree. It makes sense that we have a whole bunch of colors over here, a whole bunch of colors over here, you know, because we use more colors, we use certain colors more often than other colors. Now, I realize this is between 0.5 and negative 0.5, and some people might not like that notation, but that's okay. For now, we're just kind of keeping track of everything. The idea is that we've stored all of the particle data as, how do I put this? We've stored all the particle data as basically space in RGB, which is basically XYZ, and we've created an Octree for this. Now what we're going to do is we're going to go through and redefine the image with our Octree data. So the idea now is that we're going to write out the data with our Octree, and basically any image, we're basically going to take the color, we're going to find that color in the tree, and then we're going to say, okay, we're going to approximate that color as another color. So we're going to approximate that color as the color closest to it that we actually want to use, so the average color. And so the idea then is that we'll be using like these big boxes here. Let me see. Only works with PPM images when programming. I guess he loves edging in the state of no available disk space left. Okay, so what do we have here? Let's go ahead and Control D here. And this looks okay. So I want to run a new plot just on its own, and I want to splot out. Let's do pout.dat. Here we are. So here's all the particles. You'll note that we have, this is an RGB space. So we have red going this way, green going this way, and blue going up. So you'll see, okay, we have everything kind of centered appropriately. We have a whole bunch of colors in here. Okay, so these are the colors that we're working with. Again, we'll do some visualization of this a little bit later on. But for now, here's all the colors that we have. One thing that does kind of bug me is that we're so close down here to the bottom here. So that means we have very little green. Is that true in the image that we're looking at? Let me check. I just realized that was slightly off. Sorry about that, guys. So let me go into Mirage, and let's do Flower Power 2. Here's the image. Now there's a lot of green in that image. Yeah, there's a lot of green. Look at that green. So, that's something to look into, but I think for now it should be okay. Now, what do I want to do? I want to go down real quick, and let me see what we have here. So we have SGC out. 1 second, let me see. Number of pixels. So actually, this isn't the number of pixels. I just realized that. It's the number of pixels times 3, which is important to make the distinction for. So, now what are we going to do? We are now going to create a new function for compressing the image into the appropriate color space. So let's do that. Let's go into vi color quantization.h, and let's go ahead and create our new function. So particle output, Octree output, all that seems okay. Now, what do I want to do? Should we just call it compress image, or should we call it rewrite, quantize color? Oh, let's call it quantize color. Why not? Void RK search. don't think we have that anymore. So let's go here and let's say function, 1 second, to quantize the color. Now, one important thing to note here is all of the node structures in our Octree have a center of mass, right? That center of mass will be the approximate color of all colors within its box, if that makes sense. So the idea then is like, let's say we have, you saw the boxes, right? So we have some box up here in the upper right-hand corner, lower left. In fact, let me just move over here. So we have some approximate color for each of these boxes here. And that approximate color is the color that we're going to be basically turning all the colors in that box into. So we'll say, we'll basically go up the parent chain until there are no parents left, and then we'll use that color. So it's just a recursive search upwards until we hit the resolution depth that we need. If that makes sense. I hope that makes sense. Sorry if that doesn't. Let me see. If you have questions, let me know. The idea is that we split our space up into a whole bunch of boxes. We have approximated the color in every single one of those boxes. Now, every time we go through a pixel and we find that pixel color, we approximate that pixel color as the approximate pixel color in the giant box, right? So in this way, since we have 8 big boxes that we're working with initially, we can approximate just 8 colors in the image. And we could go further and further down as we go, as we have more and more pixels, if that makes sense. So the idea is that we have 8 approximate colors for the entire image, and we go from there. Of course, we could have more or less depending on how we've split up the Octree. Okay, so let's go over here. Now, what do we want to call it? Function to quantize a color. So let's go down here and let's just call it a void function. I don't see any reason for it not to be void. And we will say quantize color. Okay. What do we need to read in? We need to read in a couple of... Yeah, exactly. You have to think in the box. What do we need to read in? We need to read into the Octree data. So we're going to say node star root. Oh, wait. Is it star root? Let me think here. Yeah, I think that should do it. Yeah, that should do it. Then we got std string. Let's see, what else do we need? We have the Octree data. I think that's all we need. So std string, and we're going to say out file should be okay. Let's do it that way. Let's grab this, and let's put it at the bottom of our file. There we go. There we go. Write this, and let's do the color quantization. Okay, so what are we gonna do? Oh shoot, I forgot one big major thing. We have the C image data. We should probably read that in too. So, because without that, we can't really write out an image in the end, right? So, let's do it. So we need to read in, what is it? C image float, I think is what it is. Yeah, C image float. C image float. Okay, and we're gonna read it in as image. std string out file. Now, I gotta think about this. There should be a way to parallelize this a little bit easier. I'm just not sure how to do that right now, so we'll kind of look into that in a second. So let's go down here. Let's use C image float. Float. Okay, and we're gonna say image. Good. Write this, go over here, right and quit, and let's make that. Just to make sure it makes. No problem. Good. Seems to make just fine. Now, what do I need to do? I'm going to define C image float, and we're going to say out image. Let's do this. Vi, 1 second. Color quantization.h. Let's go down to the end here, and let me see. Color quantize ampersand. What do you code for work? For work, I typically code something that's known as a... Oh, how do I put this? So I do a whole bunch of superfluids for work. So let's say out image. In fact, we don't even need to do out image. Let's just go through the actual image. So I work on what's known as a Bose-Einstein condensate for work. So what I do is I basically put the entire condensate, which is basically a bunch of bosons that have been condensed into their ground state on a grid, and then I simulate the internal dynamics of that particular system. And basically, it's just it's a pretty simple system to work with in a way, because all we have to do is simulate the grid and do some FFTs, and we're done. That's kind of how it's done. It's kind of a long code, and in fact, you can see it. Let me just go here. Here is my channel. If you go to info, you go down to... Oh, actually, it's not on my GitHub, is it? 1 second. Go to my GitHub account. The actual code is under someone else's name right now, so GPUE is the name of the code. 1 second. GPUE. Here it is. This is the code that I currently work on for work. So if you're interested, feel free to take a look at that. Totally up to you. Okay. So now we have to iterate through... Oh, sorry about that. Iterating through the image. Good. So what do we want to do? Well, we're going to do the same thing we did before. So it's going to be the following. For int I equals 0. Then we're going to say I less than image.size. Let's say width. And then we're going to do plus plus I. Next loop. For int j equals 0. J less than image.height. Plus plus, oops, sorry about that, forgot a semicolon, plus plus j. So this is going to be going through all the pixels. Now all we have to do is redefine the pixel for each color. So let's think. What is the best way to do this? Well, we have all the bounds of the Octree boxes, right? Maybe the best way to do this is we read in the pixel color, we determine which box it's in, and then we just go from there. So where's our inbox command? Let's see. We should have an inbox function or something like that. So we just recursively search to find which box it's in, and then we go from there. However, this is relatively straightforward for now. So all we have to do is go through. Yeah, this should be pretty easy. So here's what we're going to do. We are going to find an RGB value one more time. Yes, an RGB value. We're going to create a vector with that RGB value, and then we're just going to go through all 8 children of our root node and see which box it's in. Now, we can do further approximations later, but for now, this will work okay. And this is going to be a majorly underwhelming test to start. Like, you guys are going to be super not impressed with the first couple tests. Again, we have to find ways to parallelize it, we have to find ways to make it faster, things like that. But for now, this should work okay. So what am I going to do? I'm going to go up to what we did before. Where are we here? Here it is. Float RGB. And of course we're casting these floats as doubles. I now understand what you guys were saying before. That might just be how it needs to be done. So let's grab these guys. Let's go down to the bottom here. And let's paste it out. Let's remove these lines here. And let's see, what do I want to do? I want to grab these guys and put them down here. There we go. Although, geez, I don't have that bad of a lisp. Okay, so there's one thing I wanted to point out. At work, we recently basically turned our GPU box into an Arch Linux machine, which is great. I love having an Arch Linux machine. Like, it's seriously awesome. Because Arch Linux is what I use here, and I'm used to it, you know? So I was there at work, we have our Arch Linux machine, and I found out that even though I'm using a Mac on my own workstation, right? So I have a Mac, I'm SSHing into the Arch Linux machine to do my work. I found out that even though I'm using the Mac for the main GUI, I can still use the middle click paste in the terminals, which is great because that's one thing that I absolutely miss from Linux. It's one of those things that I find incredibly useful for working and stuff like that. Okay. So we have the RGB data. What am I doing? Oh, now we're going to check to see if it's in a box. So let's say for, and let's just do it this way. We're going to say auto child in each of these root node images. So we're going to say 1 second. Root pointing to children. That's it, I think. Maybe I'm wrong, but that should be okay. Okay, so now we're going to say if, and I think we have an inbox command. So let's just go ahead and define this as a color vector. So we're going to go up here, we're going to say vec. I usually use Control-Shift-V for pasting in the terminal and regular copy-paste commands in Vim. Yeah. Okay, so let's do color P. And we're going to go up here and we're going to define color P is going to be equal to vector position. So vec of RGB. There we go. Now, what do I want to do next? I want to say, let me see, where's our inbox command? What do I need to read in there? Particle P, current, there we go. So we're going to say if we are in box. Yes, that's what I want. G, Dan and Beard, if you do a lot of SSHing, check out Mosh. It's a wrapper around SSH that's great for keeping a connection up and running. Also makes it feel more responsive if your SSH is reaching out to a box with a bad connection or a lot of network latency. Yeah, sounds like I might look into it. Honestly, the SSH command works just fine for me. The only problem is sometimes when you do SSH-X, sometimes the X11 forwarding is a little bit slow, but that's okay. So we have our inbox. So we're just going to say if, and let's see, we need to read inbox child color P. Now, one thing to note, this is a if inbox color P, and I just realized it needs to be a particle, not a vector. So let's go up here and let's change this into a particle. And just let me check this to make sure. Inbox. Here we are here. Yeah, it has to be a particle, which is okay because we've already defined particle stuff like that before. I'm just going to grab what we have up here. Color data is equal to particle. 1 second. In fact, we already have color data, don't we? We returned color data. Why don't we just read color data in, since it's a bunch of particles, and then we're set. And I just realized one thing that I did wrong here. Color data of I, I'm constantly redefining color data of I. So what I need to do here is I actually need to say color data of I. I'm gonna have to think about this real quick, but let's go ahead and read in color data instead of the CImage, and that saves us some time. Sorry about that, guys. I should have recognized that was going to come up. So CImage, again, we probably don't need. We just need a vector, std, vector of particles. And what did I call it? I think I called it color data. Yeah, this is what we need. And then we'll pop this down there. Okay, now what we need to do. I never just liked it enough to change it. Okay, we actually also need to read in the other thing too. So let's read in CImage float. And we're going to say image. Here we are. Let me see. I didn't do a lot of pasting from system to clipboard. Fair enough. Okay, so let me go over to quantization.h and let's add in the new vector particle color data. Where are we here? What am I doing? Quantize color, let's add it in. So I grab this guy, paste it over there, add in a couple spaces. There we go, right this. Now we're gonna go down here, instead of doing float RGB like I was doing, let's just kind of do, let's see, color P is equal to vector, I already have that. So all we have to do now is for inbox child color P, but this is just going to be color data of our iteration that we're currently on. Now, one thing I have to point out, it's not actually I've been doing this incorrectly. I will fix that in a second. We're going to say, I do wish someone would solve a single global clipboard in Linux though. I realize it's tough to do with security concerns, but I never need more than one clipboard. I'm not actually sure what you mean by security concerns there. So what we're gonna say is, what do I want here? Okay, so now we need to change the color of our image to match the color that we want it to be. So we're going to say, I guess it's going to be image of I and j of 0 of 1 is going to be equal to color data. Again, we're going to fix this I problem in just a second, of I dot P dot X. And then we're going to yank this and paste it. Oh, yank, paste, paste. And we're going to do the same for green and blue. Green. Oh, sorry. This should be a 2. No, this should be a 1. This should be a 2. And this should be a 0. There we go. And this should be P dot Y. And this should be a P dot Z. Okay. So now we should be updating the image. And then all we have to do at the very end, after all these for loops, is write it out. So we're going to say image dot save. And we're going to save. Ave. And let's do a new file name, which we're just going to say out.png. Oh, never mind. We have out file. Out file. Okay. So, last thing we need to do is figure out what to do with the image data. Thanks. Open link. Okay. So there's one thing that I realized we did incorrectly that we now need to go up and fix. This is in generating, or we've made the same error twice. It might not be obvious what the error is, but I will show it to you in just a second, and then it should, I hope, be a little bit obvious. Okay, so first of all, we've defined color data as image.size. However, this is 3 times too large because they save RGB kind of together. So what I want to do, let me see, is this. Let's divide this by 3. Okay, so this should give us the appropriate size there. Image ij should be okay. Now we want to go down here and say color data of I plus, let's see, I will be the width, j will be the height, right? So we're going to go through all of the height, all of the height, all of the height. So it should be I plus j times image dot height. That's what it should be, I think. So let's go down here real quick. And let's try that again for these guys. Color data of I plus j times image dot height. Okay, now let's go over here, right quit, let's make that. Okay, so we have a couple of problems. Image dot height. Let me see. Invalid use of member function int cmg library cmg height. Did you forget the, okay, I sure did. Let me go up to the top here, scroll down just a little bit. Yes, that's totally what I did. I apologize for that, guys. Let me see. It's not a huge thing, but my understanding is that no one has gathered around a single standard clipboard for security reasons. It's not a huge factor, but it causes many security hardliners not to play nice, is my understanding. I will take a look in just a second. Let me just make this, and we'll see what happens. Okay, so that broke again. Let me just clear a couple times, and let's try making it one more time. Okay, error, cannot convert image height, if inbox. Okay, what did I do wrong? Cannot convert. Let me see. Cannot convert new allocator particle to particle star for argument. 1 second, let me think. Particle star is what we need. What do we have? We don't have particle star. So I guess what we should do is maybe change the inbox command. Let me see. So currently inbox requires we have a particle star. For auto p in current vector positions, let me see. Current pointing to vector position. What do we need? If in child p, wait a minute, let me go down here and let me see what we have. Root children, color data, if inbox, color data. Oh, I'm seeing the problem here. Definitely seeing the problem here. Okay, so here's what I want to do then. Let me just create a second inbox command with what we need in it, just to make this easy. So where are we? We're a second inbox command. Let's grab this, go down here, paste that, and just change this to particle P. Yeah, I guess we can have %P, doesn't matter. Let's try making that. Let me see, error has non-pointer type. 1 second, let me go to non-mention call, cimage library, image save. 1 second. Oh, okay, I know what I have to do there. This needs to be changed to .c string. Okay. And then what else do we need to change? We need to change error has no pointer type. Let's go to 147. Okay. Return P. Oh, obviously. P is what we're reading as PX. So I guess what we need to do, particle P, is change all these to dots. That was bad notation on my part, but that's okay. Current P, yep, so let's change these all to dots and see what happens. Super bad notation on my part. My apologies, guys. Give this guy a second to make. We're going to see where it breaks, and then we'll go from there. Oh, seemed to work just fine. Fantastic. Okay, so now what I want to do is open up with new plot, the last guy that we plotted. So let's do out.dat. There we go. That looks a little bit nicer. More particles. Okay. So let me just output something else. So let me go up to the top. Where is main? And let's see, what do we have here? We have, where am I outputting? See how number of pixels is that? But actually, I want to yank this, and I want to go down here, pvec image read. I want to say, pasting it here. Oops. Pasting it. Oh, dagnabbit. Yank this guy. Yank the entire line, go down here, paste it underneath, add a space there, and instead of being image.size, I actually want pvec.size. There we go. So let's go ahead and get rid of this guy. And now what I want to do is, after Octree output, I want to do the function that we just wrote, which is, 1 second, where are we? Let me go to vi color quantization.h. Let me go down to the bottom. We called it quantize color. We basically just need to read this guy in there. So, quantize color, and we need to read in root pvec image and out file, which we're going to call out.png. I might need to save it as something else. We'll see what happens. Write this, right quit, and let's make that. I'm not sure if... Yeah, okay, so let's try something else then. Let's try BMP, because that's my first bet. But actually, let me just go down here and let me just remove this real quick. Okay. So it still gave us an error, so let me go ahead and comment that out. Let's go ahead and make this. I'm not sure what the error is. Oh, Let me see. Color quantization. In main. So I think what's happening here, it's a linker error. Oh, is it? Oh. Maybe it's because we don't have the inbox command in both functions. Let's go to color quantization.h. Let me see if inbox is in here. It is, so maybe we just put an additional inbox in here. Particle P. What else could be the issue? Let's go down to quantize color. Let me see. Node root, color data, image. Oh. That could be it. Give it a second. Okay. Make error 1. Let me see. Candidate inbox node particle. Let me see. Is ambiguous. Call for overloaded function inbox node star allocator particle. 1 second. Info included from color quantization.cpp 15. Candidate bool inbox node star particle ampersand. Oh. Color quantization.cpp. Oh, I know the problem. Let me go to color quantization inbox. I think I put an ampersand here. Let's try that. Okay, so it seems like everything happened. So now let's go down here and let's see if we can output it to a file. Okay, let's make it. And that is 7 o'clock exactly, and color quantization looks like it's pretty close to being done. So let me do Mirage. I don't remember what I called it. Out.bmp. Okay. Okay, well, it's broken. That's good to know. Okay. But what should we do? Okay, here's what we're gonna do, guys. The color quantization is mostly done, but it's currently not quite there. So there's something there missing that I need to think about a little bit. So if inbox child color data j times image.height, it could just be that we're not going through everything appropriately. Like just that I plus jk. Yeah, right, it wasn't quite right. So I'll show you what it was to begin with. In Mirage, flower power 2.png. This is what it was to begin with, and that's what it was before we cut it. This is what it turned into. Just to scroll in, we kept some of it, but not all of it's there. So that means that some of it's black, and I'm not exactly sure why. So this is something I will kind of look into either today or tomorrow. We got a lot left to do. Well, not that much left to do, actually. We're pretty close to being done. Most of the color quantization has been written. However, I think I'm going to go ahead and leave it at a bit of a cliffhanger for tomorrow. So I will be here tomorrow again, same time, 5 o'clock in the morning my time. I don't know what time it is your time, but 2 hours before whatever time it is right now. And we will do some color quantization stuff then. For now, I want to just go ahead and quickly go to my channel. And if you guys want, let me see, where are we? Creative. Just let me know. If you guys want, I can totally host someone at the end of this stream. So let me see. I haven't done this in a while, just because I haven't done it in a while. But if there is someone you want me to host, let me know, and I can totally host that person. So I'll give you guys a few minutes to find someone, and if you guys don't have anyone you want me to host, that's also fine too. I totally understand. Up to you guys. Okay, so now let me see. Just as a quick note, let me go up to the top. And let me go ahead and fix the notes for tomorrow. So let me see, we can remove most of this stuff. And let's kind of write down some things here. So first thing we need to think about is figure out why output image is all black. Alright, I'll see you around, Guster, and thanks for coming in. And then what else do we need to do? Visualize. Find way to better visualize. What do I want to say? How about the particle? And 1 second. Okay, yeah, sure, I can host him. So we'll do particle data, and what's the last thing I need? So particle data and also Octree boxes. Let's try maybe Blender? Question mark. Oh no, not enough space on the line. Crap. Find a way to visualize particle and Octree boxes. What I'm thinking about doing here is the same thing we did before with the particles all over the place, except this time actually give the particles the appropriate color. And then putting in the Octree box on top of that, which shouldn't be so bad because it's pretty easy to make wire boxes in Blender. So we'll see how far we get there. Good. So that's about it for today, guys. I will probably not commit this to GitHub just because it's not currently working, but we can commit it a little bit later. At this point, guys, I'd like to thank you so much for watching. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we continue working on the color quantization. Should be finishing it up, I think, tomorrow, if not the day after that. And then I'll make a quick YouTube video on the color quantization stuff before going back to the Barnstot algorithm with basically galaxy simulations and stuff like that. Should be a lot of fun. What's going on with the galaxy simulation next is, of course, visualization with OpenGL, which I've never done before, so it's going to be kind of messy. Hopefully you guys will stick through that. Outside of that, guys, I will host Adam 13531, and that'll be that. So thanks, guys, so much for watching, and I'll see you next time. Bye, guys.